Hello everyone, we are Tomoyuki Akaho and Nakadate, graduate students from Tokyo University of Science, Japan. We are going to present our research, the title of which is The Directionally Guided Photon Flow in Real Space, a Virtual Reality, an ongoing subjective experiment on the perception of physical light field. This is an outline of this presentation. First, we conducted a controlled experiment to verify whether directionality guided photon flow can help us to understand the physically correct light field more accurately than original spherical photon expression. Next, we also conducted interviews with practitioners and summarized their comments on how to improve the photon flow for using it in the actual architectural and lighting design process. Photon flow, which have been presented in our previous study, visualizes the lighting environment in 3 dimensions in space. It's calculated by using the boring photon mapping algorithm. But photons should neither be scattered nor absorbed by the mist to preserve their energy and trajectory within the environment. The extinction sigma determines the density with which photons are deposited. High values give a poor distribution. The lower, the better, but slower. Photon flow is generally observed using a 2-dimensional display, so it is sometimes difficult to visually grasp the positional relationship between the light source and the photons, because they appear to overlap in a flat plane. So we observed photon flow in 3 dimensions using a head-mounted display last year, but the problem remained under certain conditions. This is a summary of the last year's experiments. Under the condition with a directional light source, the prediction accuracy of the physically correct light field increased when the photon flow was observed in the virtual reality space. But in the chromatic space, prediction accuracy was lower than in the achromatic space. On the other hand, it was difficult to predict the physically correct light field by observing the photon flow in virtual reality space under the diffuse light sources in both achromatic and chromatic spaces. Especially the directionality was greatly misperceived in there. Based on the last year's results, we propose a directionally guided photon flow. The difference of this new expression is that the information of the movement of direction of each photon is output and reflected in the shape of the photons. We hypothesized that the directionally guided photon flow would improve the prediction accuracy of the light environment compared with the original spherical photons. This section describes the procedure for creating the directional guided photon flow. A boring photon map is created with the mkp map command. Here, the option ME defines the mean density of photons along a array. In this study, unlike the previous way of making photon flow, the pmap command not only outputs XYZ coordinates and RGB color information of each photon, but also outputs the XYZ vector information of each photon's direction of movement by using -n option. After that, the game engine, Unreal Engine, is used to display the photon flow on the head-mounted display. This slide shows the videos of the photon flow in the church in Japan, which is famous for its unique light, outputted to the head-mounted display. The video on the left is the spherical photon flow presented last year, and the right is the conical photon flow, to which directionally is added. The light entering through the side opening is colored blue, and the light entering through the front openings is colored yellow. Hendrik clarified that there are physical and visual light fields. Physical light field means simply the physically correct light field. On the other hand, visual light field indicates the light field perceived by people. By understanding the physical light field, it would be possible to predict how light will hit an object in a certain space and how it will finally appear. In this study, we examined whether adding directionality to the photon flow would improve the accuracy of prediction for physical light field. I will move on to the explanation of our new experiments. We picked out some lighting conditions in which the prediction accuracy of physical light field was not so high, even when the participants observed the photon flow using head-mounted displays in the previous experiments. A total of 3 conditions were prepared. A chromatic space with one directional light source installed in the center of the ceiling, and an achromatic and chromatic space with one diffuse light source installed in the center of the floor. The experimental and evaluations method was almost the same as the last year's and already explained in the previous workshop. But I'll repeat it because it's a bit complicated and difficult to understand. This experiment employed the white sphere method to capture the light field, which was proposed by Kazuto. Participants predicted the shade distribution on a hypothetical white sphere, which was not actually installed in the presented space. This section describes the 3 methods for presenting the experimental space. In the first method, participants observed rendered images that reproduce real spaces. In the second, they looked at the photon flow on a 2-dimensional display. And in the third, the spherical and conical photon flow were observed on a head-mounted display. The estimated light field by the first method can be said as a visual light field. After the observation, they inferred the shade on a hypothetical white sphere, which was assumed to be at the position indicated by the experimenter. Hypothetical white sphere was not actually displayed on the monitor or in the virtual reality space. In this presentation, we will refer to this position as evaluation target position. Next, I'll explain the evaluation method. White sphere images rendered from a horizontal direction represented the light field at different locations in the space. Participants compare the shade on white sphere images on a monitor with the estimation of the shade on a hypothetical white sphere. Participants judged whether the shade presented on the monitor was correct and decided incorrect as one on the hypothetical white sphere. This year, 3 positions were set for the hypothetical white sphere: high, middle, and low, as shown in the figure. Participants predicted the shade of the white sphere when they observed these evaluation target positions from the horizontal direction. As with the experiments conducted last year, we used 3 indices such as directionality, intensity, and diffuseness to confirm the extent to which participants were able to estimate the physical light field when observing the photon flow. For the directionality, the angle between the physically correct shade and subject estimated shade was calculated. As for intensity, it is determined from the absolute value of the logarithmic difference between scalar elements in the physically correct shade and the shade estimated by the participants, indicating the ratio of former to latter scalar elements. As for diffuseness, we calculated it using the vector scalar ratio proposed by Kato. When the white sphere is illuminated by a collimated beam of light, the value is 0, and when it is uniformly illuminated, the value is 1. Now, I'll move on to the explanation of the results. First of all, this slide shows the types of participants. In the experiment conducted last year, all participants had already had multiple experiences of predicting, shading, or observing the photon flow. On the other hand, in this year, half of the participants were naive and saw the photon flow for the first time. This slide shows the comparison results between experienced participants and naive ones in observing the photon flow. As you can see, the experience had a significant impact on the error. Since all of the participants were experienced in last year's experiments, only the data from 9 experienced participants of this year's experiment were extracted for the following comparative analysis. To compare the data from 4 groups, the one-way analysis of variance was first conducted, followed by 2 keys honestly significant different tests. These are the results of the directional light source condition in a chromatic space. Statistically, significant differences were observed for all indices at position H and M. On the other hand, there was no improvement in prediction accuracy for the position L. These are the results of the diffuse light source condition in an achromatic space. No improvement in prediction accuracy was observed at any of evaluation target position. These are the results of another diffuse light source condition in a chromatic space. As with a chromatic space, we couldn't find out any improvement in prediction accuracy. But as to the intensity and diffuseness, in the fluoride condition, the absolute values of the error are much lower than in the spotlight condition, regardless of which observation method is used. This indicates that the participants can read physical light field accurately with respect to intensity and diffuseness, and further improvement would not be necessary. This is a summary of the experiments. Under the condition of a directional light source, excluding positions with high proportion of indirect light, observing conical photon flow in virtual reality space improve the prediction accuracy of the physical light field. On the other hand, in the case of a single diffuse light source, it was still difficult to predict the directionality of the physical light field by observing the conical photon flow in virtual reality space, both in achromatic and chromatic space. The left picture in the green box is the physically correct image at position L in the directional light source condition. And the other 2 pictures in the white boxes are the images that lots of participants judge correct shade. 33% of the participants judged images with significantly different directionality or intensity to be correct. A small green sphere in the figures shows the correct position of the target, and white spheres numbered 1, 2 shows the position that lots of participants misjudged the shade on them to be correct. When the evaluation target position was far from the light source, distribution of photons became low density, and participants more likely underestimated the direct and indirect light reaching the target position. Then, in case that image outside the light distribution angle is selected, the effect of reflected light from the floor becomes relatively stronger, resulting in a large directional error. This is a diffuse light source condition. There are no significant differences in the presented images, but there is a 35-degree angle difference between the first and third images from the left. This is the condition for position M. Similar to position H, while the intensity and diffuseness do not change significantly. There is a directional error of over 30 degrees. I will explain the cause of significant directional error. The presented images on the monitor was tone mapped to have the same luminance as in the real space. But those images were too dark, and it was difficult to participants to distinguish between correct and incorrect images. So the misjudgment may have been due to misinterpreting the directionality of the presented images rather than incorrect predictions based on observing photon flow. There is a high possibility that there was an issue with the presented images, so we would like to revisit this matter in our future experiments.
From this section, I'll report the result of a gravitational survey on the photon flow, which was conducted last winter. The purpose of the survey was to find out whether the directionally guided photon flow could be used in architecture and lighting design, and to identify the areas of improvement of the photon flow expression. A total of 21 practitioners attended the survey. 4 of them were architects, 9 were lighting designers, 2 were facility designers, and the remaining 6 were light environment engineers. A participant first received an explanation on the photon flow and put on a head-mounted display. He or she moved freely in the virtual reality space to observe the photon flow, then answer several questions. This is the directionally guided photon flow we let them observe, which had to spotlight with different color temperatures and beam angles. The left spotlight in this picture had 2700 Kelvin color temperature, called warm light in here, and 90-degree beam angle, which is different to narrow. And the right one had true light that is 50,000, 5000 Kelvin, and wide 34-degree beam angle. At first, there were 2 questions the participants should answer with numbers. Question 1 was, what is the proportion of warm light to total light incident on the translucent sphere? We use a translucent sphere this time to point out the evaluation target position. As you can see in the picture, the translucent sphere was positioned just close to the border of the light beam. So if there is no information like photon flow, it would have been difficult to read the effect of light on the sphere. And question 2 was, what is the proportion of indirect light to total light incident on the translucent sphere? This is the result of the first question. As you can see, the median values were not so different among question groups, and they were close to some extent to the physically correct values. Next, regarding the proportion of indirect light in the sphere, the reality was observed among participants, but we can see that some lighting designers to answer almost correct value. But most of them underestimated the proportion of the indirect component, and this matches the previous report on the perception of light beam. We let the participant observe the photon flow and answer this question, just for extracting their comments and opinion on photon flow. So we cannot jump into any conclusion from this simple question and answer at the moment. But we could say since the photon seeing the photo flow helps to understand the light field, but it will still need some experience for utilizing it. Next, I will share the result of the question 3, which is, was it easy for you to judge the proportion of warm light and indirect light by observing the photo flow? Please also explain the reason for that. Some participants agree that the addition of directionality to the photon helps to understand the overall picture of light in space. On the other hand, a few participants said that the tip of the cone should not point to the direction of movement. The current light acceleration will be more referable. Question 4 was, in what specific situation could you use the photo flow in actual architecture or lighting design? And question 5 was, could you give us any ideas on the areas for improvement the current photo flow expression? This graph shows the result of question 4 on the expected applications in practice. There is a strong interest in using the photo flow as a presentation and communication tool in the design process. Architects said that current illuminance distribution images are sometimes difficult for clients to understand the concept of lighting environment or window design. So they search photon flow expression could add some power or persuasion to their presentation to the client. On the other hand, some lighting designer and facility designers said they would like to use it as a communication tool for presenting their concept of lighting design to architects who are not specialists on lighting. As a design support tool for lighting environment or indoor spaces, some architects said they could use it to check the light spread after the light passes through lines with different slant angles or after it reflects on the light control system, such as light shelters. Some lighting and facility designer pointed out that photon flow seems useful as design assistant to for spaces where indirect light is crucial, such as museums. The left picture is a new display room in Adachi Museum of Art in Japan, and the right image is a photo flow of that lighting environment. The concept of the lighting design was to make the totally non-direction a uniform light environment where there is no difference in brightness all over the room. He expected to use the photon flow in his future design process to check the uniformity, especially around the artwork positions. The last topic is about areas for improvement of the current photo flow. As you can see, there are relatively lots of comments for interactivity and animation. Some architects said that they would like to check the effect of changing the light position instantly, but it's difficult at the moment. And some participants proposed the animation in which photons move in their direction of movement. They said it could make the flow even clearer. We'll present a sample of this kind of animation later. Another proposal was superimposing the photon flow on the horizontal illuminance distribution map. Basically, all the lighting designers are familiar with the two-dimensional illuminance maps. So they thought the combination of illuminance and photon mark will help them to understand the light environment more intuitively. This slide shows some issues or negative opinions on the photon flow. First, some participants pointed out that actual brightness was difficult to read from the photon flow alone. And that I think that too. And we need some judgment criteria or reference points which make it possible to anchor absolute values brightness. And one of the objects who does not specialize in lighting horizontal illuminance marks and sees the image are enough to understand lighting environment. But that will be controversial. In this research, we proposed a method to add the directionality to photon flow. Using a directionally guided photon improves the accuracy of prediction when directional light sources are used. Prediction is difficult at position and indirect light and still challenging even when a directional light source is distant. Under the condition of diffuse light source, there is a high possibility that there is an issue with the presented image, so it needs to be reconsidered. According to subject experiments and interview surveys, it is suggested that having an animation function makes it easier to understand the light environment in location with a high proportion of indirect light. This video was created by gradually moving each photon in its direction of movement. By moving photon, it is easy to intuitively understand in what direction photons around the light source is moving. In the future, we plan to add new features or presenting the direct and indirect components separately, as well as an animation function that can represent reflection on the walls and floor. We'd like to try to apply transient photon method to this kind of expression in future. Thank you for listening.